Few-shot class incremental learning is a scenario which does away with preconceptions of complete and abundant data. First, we show our model some base data. This is often ample data such that the model can learn a good representation. After this pre-training session, we conduct an incremental session. In this example, we expose our model to just 2 samples for 3 completely unseen classes. This sparsity of data is why this setting is prefixed with few-shot. We now train our model such that it learns to predict these new classes. After this training, we evaluate our model to predict all classes from a combined testing set. We do this for a total of m sessions, with each session having only a few classes with sparse representation. We can imagine use cases for this in self-driving cars, robotics, and AI applications, where completeness of data at one single moment is not guaranteed. But with this, we introduce some problems. Firstly, we have catastrophic forgetting. Catastrophic forgetting refers to previously seen classes being forgotten. In trying to mitigate this, methods become base biased. Second, given that we only have a few examples per incremental class, we can suspect that there will be difficulty modeling these few-shot classes. This problem is known as intransigence. Overfitting can be a side effect of this. In this work, we tackle these challenges via orthogonality and contrast. We first learn a robust representation followed by 2 alignment phases, which allow strong performance. First, we have a look at our pre-train phase. Our framework deeply relies on contrastive learning to form its underlying ability to represent data. To this end, we'd first define a model with a backbone F, which may be a ResNet, and a projection head G, which is a simple 2-layer network. To visualize the learning process, let's pass some images from the stored dataset into our backbone. Our images get projected onto the feature space as vectors, which are normalized to unit length. We visualize our feature vectors as color dots on a circle. Let's now introduce our loss function. We use a combination of supervised contrastive loss and self-supervised contrastive loss. With this, our feature space may look like the following at the end of the pre-train phase. Supervised contrastive loss intends to bring features of the same class closer together, whereas self-supervised contrastive loss allows for instance space contrastive loss. This learned model provides better transfer and low intransigence. Next, we see the base alignment phase. To introduce elements of space reservation, we need to sample locations which could possibly host our feature vectors. On the left, we have our unaligned feature space from the pre-training phase. In this example, we generate 8 pseudo-targets. Let's introduce our features to this orthogonal targets. Let's in fact look at a consolidated view of our features for convenience. Here we visualize the mean of the features from each class. Also for convenience, let's visualize our orthogonal targets as stars. We use Hungarian matching to find the optimal assignment between the class means and class targets. Here are the assignments we make for this set of classes. Note that now we have some assigned targets and some targets which are left unassigned. This will be critical in creating margin and reserving space. Finally, let's align these class features to their targets. For this, we use our novel OrCo loss. OrCo loss optimizes only our projection head G and keeps the backbone frozen, as this helps mitigate catastrophic forgetting. Finally, here is the alignment we wanted. This was the location before assignment, and this is now the new location. Let's have a quick look at OrCo loss. The OrCo loss consists of a novel formulation of supervised contrastive loss, cross-entropy loss, and an orthogonality loss. The orthogonality loss applies a geometric constraint to class means to be orthogonal to each other, as follows. For basic alignment, we look towards cross-entropy. Our contrastive loss component, named perturbed supervised contrastive loss, utilizes the assigned targets in the positive and other pseudo-targets, and specifically their perturbations in the negative set. With this, we get a push and pull effect as shown and this induces higher margin. So going forward with this formulation, we reduce forgetting, induce high margin between classes, and reserve space for incoming classes. Now that we have our framework ready, we can apply it to few short incremental classes. We do the same as before. We freeze the backbone and train only the projection head, introduce new data alongside and some exemplars from the previous sessions. From the set of unassigned targets, find the optimal target, apply OrCo loss, train and align, and with this we reap the same benefits as before alongside high generalization on incremental classes. We meticulously benchmark OrCo against 8 other methods and find a consistent harmonic mean improvement. The delta in the graph shows the overall improvement over the closest competitor in terms of harmonic mean. The sessions are plotted on the x and the harmonic mean is plotted on the y-axis. Generally, the higher the accuracy, the better. We make a comparison of our method to our closest competitor, which indicates base bias and intransigence, whereas OrCo suffers from neither. The PCA projections over the 3 phases shows we are able to achieve high margin between classes, here seen on the rightmost figure. To close off, we introduced OrCo framework and looked at novelties in our loss function. We looked at our proposed supervised contrastive loss and finally viewed our state-of-the-art results.